Hi guys, and welcome back to my YouTube channel. For today, we will discuss about convergence test. In this section, we there are several tests that are useful in determining convergence. First is we have this theorem at point 2.1, the comparison test. We'll let the summation of a sub n and the summation of b sub n be infinite series of non-negative terms. That is, a sub n is greater than or equal to 0 and b sub n is greater than or equal to 0 for all n. Then we have these two conditions. If the summation of a sub n converges and 0 is less than or equal to b sub n, which is less than or equal to a sub n for all n, then the summation of b sub n converges. We have this second condition. If the summation of a sub n is equal to the positive infinity and 0 is less than or equal to a sub n, which is less than or equal to b sub n for all n, then the summation of b sub n is equal to the positive infinity. We have this proof. Since b sub n is greater than or equal to 0 for all n, the sequence t sub n of partial sums of the summation of b sub n is an increasing sequence. In part A, we have this sequence is bounded above by the sum of the series summation of a sub n, so that t sub n converges by the monotone convergence theorem 4.3.3. Thus, the summation of b sub n converges. In part B, the sequence t sub n must be unbounded, for otherwise the summation of a sub n would have to converge. But then the limit of t sub n is equal to the positive infinity by the theorem 4.3.8, so that the summation of b sub n is equal to the positive infinity. We have this example. Consider the series summation 1 all over the quantity of n plus 1 squared for all n elements of natural numbers. We have 0 is less than to 1 all over the quantity of n plus 1 squared, which is less than to the 1 all over to the quantity of n plus 1. In the example, we saw that the series summation of 1 all over n quantity of n plus 1 converges, so the summation of 1 all over the quantity of n plus 1 squared must also converge. We have this definition. If the summation of the absolute value of a sub n converges, then the series of the summation of a sub n is said to converge absolutely or to be absolutely convergent. If the summation of a sub n converges but the summation of the absolute value of a sub n diverges, then the summation of a sub n is said to converge conditionally or be conditionally convergent. We have this example considering the p series. Any series of the form the summation of 1 all over n to the power of p, where p is the element of real numbers, is called a p-series. It is easy to see that the ratio and the roots test both fail to determine convergence, but we can use the integral test. For p is not equal to 1, we have the integral of 1 all over x raised to the power of p dx evaluated from 1 to n is equal to the integral of x raised to the power of p dx evaluated from 1 to n is equal to x raised to the power of negative p plus 1 all over negative p plus 1 evaluated from 1 to n is equal to the 1 all over 1 minus p quantity of n raised to the power of negative 1 minus p minus 1. The limit of this as n is approaches to infinity will be finite if p is greater than 1 and infinite if p is less than 1. Thus, by the integral test, summation of 1 all over n raised to the power of p converges if p is greater than 1 and diverges if p is less than 1. When p is equal to 1, we get the harmonic series, which is divergent. So, the p series, the summation of 1 all over n raised to the power of p converges if p is greater than 1 and diverges if p is less than or equal to 1. This can be useful when applying the comparison test. If the terms is a series alternate between positive and negative values, the series is called an alternating series. Our final test gives us a simple criterion for determining Determining the convergence of an alternating series. The theorem 8.2.16, the alternating series test. If a sub n is a decreasing sequence of a positive numbers and the limit of a sub n is equal to 0, then the series of the summation of negative 1 raised to the power of n plus 1 a sub n converges. We have this proof. This idea of the proof is to show that the sequence a sub n of partial sum converges by considering two subsequences. The first is the subsequences s sub 2n coming from the sum of the even numbers of terms, and the subsequence s sub 2n plus 1 coming from the sum of the odd numbers of terms. And the text, there are several examples of applying the various convergence tests to a specific series. And that will be all. Thank you.